In this lecture, we're going to talk about limited dependent variable models. Limited dependent variable models are models where the dependent variable is categorical or limited because it can't have negative values or any other kind of constraint. And they are generalized linear models that we are talking about because the core component is still going to be the linear relationship between the independent variables in beta, but we're going to transform this so that we can model nonlinear relationships. Let me first refresh a little bit something that was on a much earlier slide, I think in the first lecture. The difference between the stochastic component of a model and the systematic component of a model. So if you think of the linear model, we have a linear relationship between x and beta. We multiply the x matrix with the beta matrix, and the result is that all the first x variable is multiplied with the first beta parameter, the second x variable with the second beta parameter, and so forth. And then they're all summed together. So we get a linear relationship between the x variables and the predicted value, x times beta. And the stochastic part then is that we know that the actual observations are not exactly on this linear line, on this plane, but they will vary, they will have deviations. We know that in nature there will be random other factors that play a role, and we assume that all the observations will vary around this predicted value. And in the linear model we assume that this will follow a normal distribution. So we have a linear prediction, which is the systematic part, and then we have a stochastic part, which is how these observations vary randomly following a normal distribution around this predicted part. So now we're going to move to the second half of this slide, which is the generalized linear model. We still have a systematic part, and in this case we also still have a linear combination of x and beta, but we're going to transform this. We're going to apply a function to this linear prediction to get a prediction that is not necessarily linear. And we're also going to generalize how y then varies around this predicted value. We're not necessarily going to assume a normal distribution, we can assume different types of distributions. But it remains the case that there is a fixed relationship between x and beta that forms the systematic part of the model, and that we assume that the data will randomly vary around this systematic part, and this is the stochastic part. So they vary differently. We assume that the stochastic part, there's always other factors playing a role. So even if you have the exact same prediction for x and beta, you're going to get different observations in y. If you observe the same unit in different points in time, or different units with the same predicted values, they will vary. Whereas the systematic component, it will vary between units because different units will have different values on x and therefore different predictions. They will be the same as long as x is the same. And this also leads to two different types of uncertainty. We have uncertainty around the estimates of the parameters, and these can be the parameters of the systematic part, the beta values for example, and they can be the parameters of the stochastic part. How much variation is there in how the data varies around this systematic component. So we have parameters both in the systematic and in the stochastic part, and those parameters we try to estimate, and this estimation has uncertainty. And the larger the sample size, the less uncertainty. But there is also fundamental uncertainty in the sense that even if we know beta and we know the variance of the error term, and we can observe x, then we can predict y, but we still won't know y exactly because there is this stochastic component. And that does not change if the sample size increases. There's always other factors that play a role that we have just not captured with this model. Now, early on we discussed different levels of measurement, and they are also key to keep in mind here. You might want to refresh your mind by looking at earlier slides. So we have categorical variables, where observations are in a particular category with no particular order to them, religious affiliation, party choice, and so forth. We have ordinal variables, where they are in particular categories and there is an order to them. For example, Likert scale from strongly disagree to strongly agree, or number of level of education that one might have. There's a special category for binary variables, which are really nominal variables with two categories. But when you code them as 0 and 1, we call them dummy variables, and they can sometimes act as if they are continuous. And then we have two types of continuous variables. We have the interval level variable, where we have fixed distances between observations. And we have the ratio level, where the 0 has a particular meaning in the sense that we can calculate the ratios between variables. That distinction is rarely very important. in our analysis. So so far we have basically assumed that the dependent variable are of ratio or interval scale. Now we're going to look at models where the dependent variable is binary, nominal, ordinal, maybe count variables that are on a scale but can't go below 0, and so forth. So when the dependent variable is a categorical variable and you run a linear model, you will typically get predictions that do not make sense. What does it mean to be halfway between fine Gael, fine Vol, for example, if it's party choice? You get predictions that are outside the bounds of the variable. We assume equal distances between categories that do not make sense. And we also, by definition, induce heteroscedasticity in our models. So we get all kinds of problems.